Hi everyone, today we're gonna to present our linear algebra assignment, and before that, let me introduce me and my teammate to you. Our team consists of 5 people, which is me, Zhiqing, and also Yongshan, Peiling, Meiting, and Jingru. The matrix we choose to use in this assignment is a 3 times 3 non-diagonal symmetric matrix with at least 5 different numbers, which is 1, 0, 0, 0, negative 1, 2, 0, 2, 3. It is a non-diagonal matrix as there is non-zero entries in the upper and lower triangle, and the matrix is symmetric as A is equal to A transpose. This matrix consists of 5 different numbers, which is 1, 0, negative 1, 2, and 3. So the first question, obtain the eigenvalue and eigenvectors of A. To obtain the eigenvalue of A, we have to use this equation. Ax equals to lambda x. To move the lambda x to the left hand side, we have to multiply the whole equation with identity, and we will get Ax equals to lambda Ix. So we move the lambda Ix to the left hand side and factor out the x, and we will get A minus lambda I times x equals to 0. A minus lambda I is equals to 1 minus lambda, 0, 0, 0, negative 1 minus lambda, 2, 0, 2, 3 minus lambda. To find the eigenvalue, we have to find the determinant of A minus lambda I, which is equals to 0. So we will using the cofactor multiplication in the first row to finding out the value of lambda. So the first one we get is 1 minus lambda times negative 1 minus lambda times 3 minus lambda minus 2 times 2. Second, we will get 0. And third, we will also get 0. So we will find out A minus lambda I is equals to 1 minus lambda times lambda squared minus 2 lambda minus 7. As we have to let the determinant of A minus lambda I equals to 0, which means that 1 minus lambda times lambda squared minus 2 lambda minus 7 is equal to 0. The first value of lambda can be seen very clearly, which is lambda equals to 1. For the second and third value of lambda, we can find it out by using the equation, which is lambda equals to minus b plus minus square root b squared minus 4ac over 2a. And we can finally find out that the value of lambda is equals to 1 minus 2 square root 2, 1 plus 2 square root 2. To find the eigenvector, we have to substitute the lambda equals to 1, 1 minus 2 square root 2, and also 1 plus 2 square root 2. So we first let the lambda equals to 1. A minus lambda I is equals to 0, 0, 0, 0, negative 2, 2, 0, 2, 2. Let A minus lambda Ix equals to 0. By using the system linear equation method, we can find that negative 2x2 plus 2x3 equals to 0, and also 2x2 plus 2x3 equals to 0. So from the first equation, we can find that x2 equals to x3. By substitute x2 equals to x3 into the third equation, we can get that for x2 equals to 0, which means that x2 equals to 0 and x3 equals to 0. As we can't find any value for x1, so we let x1 equals to t. x2 equals to 0 and x3 equals to 0. And we factor out the t, you can get that the eigenvector is equal to 1, 0, 0. Second, we let the lambda equals to 1 minus 2 square root 2. A minus lambda I is equal to square root 2, 0, 0, 0, negative 2 plus 2 square root 2, 2, 0, 2, 2 plus 2 square root 2. Let a minus lambda I x equals to 0. By using the system linear equation method, we can get 2 square root 2 x1 equals to 0. Negative 2 plus 2 square root 2 x2 plus 2 x3 equals to 0. And also the 2 x2 plus 2 plus 2 square root 2 x3 equals to 0. So from the first equation, we can get x1 equals to 0. And from the third equation, we can get x2 equals to negative 1 minus square root 2 x3. So we let x3 equals to t. We can get that x1 equals to 0, x2 equals to negative 1 minus square root 2t, and x3 equals to t. By factor out the t, we can get that the eigenvector is equal to 0, negative 1 minus square root 2, and 1. Third, we let lambda equals to 1 plus 2 square root 2. So, a minus lambda I will be equals to negative 2 square root 2, 0, 0, 0, negative 2 minus 2 square root 2, 2, 0, 2, 2 minus 2 square root 2. Let a minus lambda I x equals to 0, we can get that negative 2 square root 2 x1 equals to 0. Negative 2 minus 2 square root 2 x2 plus 2 x3 equals to 0. And also 2x2 plus 2 minus 2 square root 2 x3 equals to 0. So from the first equation, we can get x1 equals to 0. And from the third equation, we can get x2 equals to negative 1 plus square root 2 x3. Let x3 equals to t, we can get x1 equals to 0, x2 equals to negative 1 plus square root 2, and x3 equals to t. And by factor out the t, we can get the eigenvector, which is equals to 0, negative 1 plus square root 2, 1. Question 2. Use p that diagonalize a to calculate a power of 21. To find p, we can using the eigenvector we find just now. We can put the eigenvector from lambda 1 into column 1 and eigenvector of lambda 2 into column 2, eigenvector of lambda 3 into column 3. So to find D, we first have to find the inverse matrix of P. So by using ERO method, we can find that the inverse of P is equals to 1, 0, 0, 0, negative square root 2 over 4, 2 minus square root 2 over 4, square root 2 over 4, 2 plus square root 2 over 4. Next, we multiply the inverse of P with A and P. Lastly, we will find out that the matrix D is equals to 1, 0, 0, 0, square root 2 minus 4 over square root 4, 0, 0, 0, 4 plus square root 2 over square root 2. As we know that A power of k is equals to P times D power of k times inverse of P. Thus, A power of 21 is equals to P times D power of 21 times inverse of P. So, finally, we can get that A power of 21 is equals to 1, 0, 0, 0, 2.5652 times 10 power of 11, 6.1927 times 10 power of 11, 0, 9.1627 times 10 power of 11, 1.4951 times 10 power of 11. Question number 3. Assume that A is the standard matrix of TA such that TA is a function which will map a R cube to R cube. Obtain TA, kernel TA, and range TA. First, let's find the TA. So, TAX is equals to AX. By multiplying the matrix of A with x1, x2, x3, we can find that TA is equals to x1 minus x2 plus 2x3 and also 2x2 plus 3x3. To find the kernel of TA, we have to let TAX equals to 0 vector of R cubed, which is 0, 0, 0. So by using the system linear equation, we can find that x1 equals to 0, negative x2 plus 2x3 equals to 0, and 2x2 minus 3x3 equals to 0. From the second equation, we can get x2 equals to 2x3. And by substitute the x2 equals to 2x3 into the third equation, we can get that x3 is equals to 0. So, the kernel of TA is equals to the 0 vector of TA. To find the range of TA, we have to let the TA equals to ABC. So, by using the system linear equation method, we can find that x1 is equals to A, minus x2 plus 2x3 is equals to B, and 2x2 plus 3x3 is equals to C. As there are no any relationship between these three equations, so we can say that the range of the linear transformation TA, which is defined by the matrix A, is the set of all vectors in R cubed that can be obtained by multiplying the matrix A with any vector in R cubed.
For question 4, assume that P is the transformation matrix of P denoted as TP such that TP is mapped from Euclidean space to Euclidean space. We need to obtain TP, kernel TP, and range TP. This is our matrix P, which is 1, 0, 0, 0, negative 1, negative Z2, negative 1 plus Z2, 0, 1, 1. TP is from Euclidean space to Euclidean space. TP mapped from x1, x2, x3 equals to A, B, C. And we can get that TP is equals to x1, negative 1, negative Z2, x2 plus negative 1 plus Z2, x3, x2 plus x3. To find the kernel, by the definition of kernel TP is equals to x1, x2, x3, that is element of Euclidean space. Given that x1, x2, x3 is mapped by TP to the 0 vector in the Euclidean space. x1, x2, x3 that is mapped by TP is 0, 0, 0. Then we can get the system linear equation, which is x1 is equals to 0, negative 1 negative Z2 x2 plus negative 1 plus Z2 x3 is equals to 0. x2 plus x3 is equals to 0. By using the Gaussian elimination, we can get that the system linear equation is x1 is equal to 0, x2 plus 1 plus Z2 x3 is equals to 0, x3 is equals to 0. By solving the system linear equation, we can get that x1, x2, and x3 also equal to 0. Therefore, the kernel of TP is equals to 0 vector of Euclidean space. Thus, we can conclude that TP is a one-to-one linear transformation. To find the range, by the definition of range is equals to A, B, C, that is element of Euclidean space. Given that A, B, C, and x1, x2, x3 is mapped by TP in the Euclidean space, that A, B, C is the element of Euclidean space. There exists A, B, C being the element of Euclidean space. Then x1, x2, x3 that is mapped by TP is A, B, C. From this, we can get the system linear equation, which is x1 is equals to a, -1 negative z2 x2 plus -1 plus z2 x3 is equals to b. x2 plus x3 equals to c. As there are no relationship between these two equations, so we can say that the range of the linear transformation Tp, which is defined by the matrix P, is the set of all vectors in the Euclidean space that can be obtained by multiplying all matrix of P with any vector in Euclidean space. Thus, we can conclude that Tp is an onto linear transformation.
Now let's go to question number 5. Assume that A is the standard matrix of transformation of A such that TA is mapped from P2 to P2. We need to obtain TA, kernel of TA, and the range of TA. Given that matrix A is 1, 0, 0, 0, negative 1, 2, 0, 2, 3, the transformation of A maps the polynomial U0, U1, U2 in P2 to another polynomial 1x squared in P2, and we can get TA equals to U0 plus negative U1 plus 2U2x plus 2U1 plus 3U2x squared. To find the kernel by the definition of kernel of TA equals to U0 plus U1x plus U2x squared, which is the element in P2, given that U0 plus U1x plus U2x squared is mapped by TA to the 0 vector in P2. By setting the transformation to 0, we can get the following system of linear equation. U0 equals to 0, negative U1 plus 2U2 equals to 0, 2U1 plus 3U2 equals to 0. By solving the following system of linear equation using Gaussian elimination methods, we can get U0 equals to 0, U1 equals to 0, and U2 equals to 0. Therefore, kernel of TA equals to 0, 0, 0, which is the element is P2. Thus, we can conclude that TA is a one-to-one linear transformation. Find the range by the definition of range. Range of TA equals to B0 plus B1x plus B2x squared, which is the element in P2. There exists U0 plus U1x plus U2x squared, which is the element in P2, given that U0 plus U1x plus U2x squared that mapped by TA is equals to B0 plus B1x plus B2x squared. We let B0 plus B1x plus B2x squared is the element of P2. We can get the following system of linear equation. U0 equals to B0, negative U1 plus 2U2 equals to B1, and 2U1 plus 3U2 equals to B2. Then, by solving the following of system linear equation by using Gaussian elimination methods, we can get that U0 equals to B0, U1 equals to negative B1 plus 2B2 plus 2B1 over 7, and U2 equals to B2 plus B1 over 7. Therefore, we can get the range of TA equals to B0, B1, B2 is the element of B2. Thus, we can conclude that TA is an onto linear transformation. Thank you.
Hi, my name is Lai Pei Ling. I'll be explaining question 6. Find P prime that orthogonally diagonalizes A using the Gram-Schmidt process on the columns of P from question 2, given the Euclidean inner product. This is the column vectors of our matrix P. Before finding P prime, we need to go through a few steps. First and foremost, we need to determine whether it is an orthogonal set or not. If it is not an orthogonal set, we must use the Gram-Schmidt process to find the orthogonal set. Secondly, we need to determine whether it is orthonormal set or not. If not, we must normalize it. Okay, now let's calculate the inner product of the vectors. Since the inner product of all vectors are equal to zeros, this shows that P is already orthogonal basis. Thus, this is the orthogonal set. Next, let's check whether the set is orthonormal or not. We will now calculate the norm of each column vectors. Since there's not all the norm of the column vectors is equal to 1, this is not an autonomous set. Therefore, we need to normalize it. We divide the column vector by each corresponding norm. Thus, this is our autonomous set. Now we can get matrix P prime, which is orthogonally diagonalized A, by combining all the column vectors in autonomous set. After that, let's show that P prime is orthogonally diagonalizable by using the definition P primes times P equal to an identity matrix. After considering the calculations, it is true that P prime matrix is orthogonally diagonalizable. For the last questions, I will hand it over to my teammate for further explanations. Thank you.
Now, let us continue with the last question. Show that P prime from question 6 orthogonally diagonalize A given the Euclidean inner product. Thus, P prime also orthogonally diagonalize A given the weak Euclidean inner product, with the inner product of vector UV is polymer of the R cube to R, and the inner product of the UV is equal to U1 V1 plus 2 U2 V2 plus 3 U3 V3. So from the equation and the answer from the previous question, we given with the value of matrix A, matrix P prime, and the equation of Euclidean inner product and the weak Euclidean inner product. Now let us start with the first part of the equation, which is P prime is orthogonally diagonalize A given the Euclidean inner product. Now we can use the P prime value to get P prime transpose value. Next, to check whether the matrix is orthogonal, let us multiply the P prime transpose and the P prime. From it, we get the final value, which is identify matrix. Since the multiplication of P prime transpose and P prime is equal to identity matrix, P prime orthogonally diagonalize A using the Euclidean inner product has been shown. Next, let us continue with the second part of this question. Does P prime also orthogonally diagonalize A with the weighted Euclidean inner product? For this question, I'm using the Gram-Schmidt process on the column of P prime in R cube. First of all, let us find the column vector of P prime, and we can identify the column of P prime by writing them as vector U1, U2, and U3. Then we verify their orthogonally with respect to the weak inner product. Next, let us make the orthogonally check with the weighted Euclidean inner product. As we've known, if P prime orthogonally diagonalize A, all of the orthogonally check must get a final answer of 0. But, however, based on the calculation, for the inner product of vector U2 and U3 with the final answer of negative 1.7679 is not equal to 0, and it is not orthogonally with the weighted Euclidean inner product. Therefore, we can conclude that P prime does not orthogonally diagonalize A given the weak Euclidean inner product. That's all from our group. Hope that all of you had learned more about the matrix in algebra linear, and thank you for your time.